Welcome to part 2 of 2.1 notes. Last session we learned the definition of a limit and how to find simple limits by substitution. And today we're going to look at more complicated limits and how to find their limits, their values. So in order to do that, we need to know some of the properties of limits. And we need to know that limits, like numbers, can be added, subtracted, multiplied, divided. And so with that, I'll begin with the sum rule or property of a limit. And before I do that, we have to first state a couple conditions. So let's just say that the limit as x is approaching some generic x value, we'll call it c, of a function f of x is equal to some generic y value, we'll call it L. And also the limit as x is approaching that same c value of another function, g of x, is equal to m. So let's just say these are true. So if these are true, and I wanted to find the limit as x was approaching c of the sum of the functions f and g, well, what this property says is that I could find those limits separately and then add those limits together. So I was told that the limit as x approaches c of f of x is equal to L, and that the limit as x approaches c of g of x is equal to m. So I can find those limits separately, add them together, and then this would be the solution to the limit of the sum. So in words, you could basically say that the limit of the sum of the functions is equal to the sum of the limits. And the same is true for pretty much all the other operations. So for the difference property, you could say that the limit as x approaches c of f of x minus g of x is equal to the difference of their limits, which would basically be L minus m. So I could find their limits separately and then find that difference. If I wanted to multiply, the same would work. So if I had the limit as x approaches c of f of x times g of x, I could find their limits separately and multiply them together. And so I would just be left with the product of the limits. So the limit of the product is equal to the product of the limits. If I wanted to multiply, or if I had a constant being multiplied to a function, so let's say I wanted to find the limit as x approaches c of some constant, I'll call it k. So that's not a variable, that's a constant, a number, representing a number, being multiplied to f of x. Well, then that answer would just be that same constant times the limit of f of x. So this is a constant representing some number that stays the same, that's being multiplied to the function. That same number would get multiplied then to its limit if I was trying to find a limit. Okay, and then if I wanted to divide two functions or find the limit of the quotient of two functions, then all I need to do is find their limits separately and divide them, as long as, hopefully you guys are catching this, as long as m is not 0. Then I can divide to my heart's content. So this works as long as the limit as x approaches c of g of x, this guy right up here, is not equal to 0. Okay, and then the last property would be the power property, which is the limit as x approaches c of, let's just say I have f of x, I'll use that one, and let's say I had that whole thing being risen to a power. Whoops, I want to call that power p. So is some function risen to a power, and I wanted to find the limit of all of that? Well, basically all I would have to do is find the limit of just the f of x part, which again we said earlier is L, and then just raise that L to the same power p. And so as you can see, these properties are very simple. I can just, whatever the functions are doing, I can just do that with the limits, with the values of the limits. So let's apply some of these properties in example 3. And I want you to notice something about example 3, is that these are not specific functions. I don't know what f of x is. I don't know what g of x is. They're just generic. They're just given names. And here I'm taking the limit as x approaches b. I don't know what b is. B is just representing some x value. So this is a very common AP style question where they don't really care if you know how to substitute. You know, like in example 1, I believe earlier, we had to find limits by substituting the value into the function. We're not going to do that here because I don't know what the value is. I don't know what the function is. We're forced to use these properties. They want to see if you know your properties. And so what this is testing us on right here is the sum property, because it's asking us to find the limit of the sum of two functions. And I know what the limit as x approaches b of f of x is separately, and I know what the limit as x approaches b of g of x is separately. So basically all I have to do is add those limits, 7 plus negative 3. And then that value of 4 is the answer to part A. Here, this is testing to see if I know product rule, right up here, which is basically saying that I can find these limits separately and multiply them. So the limit of the product is equal to the product of the limits. So negative 21 would be that limit right there. This one here is using the constant multiple rule. And just so you can see right there, the k value is 4. So it's like just some number times a function. Well, I'm going to take that same 4 and multiply it to the limit of g of x, which is negative 3. And so get negative 12 for the answer for part C. And then for part D, I'll go ahead and just divide here. And I'm basically just left with negative 7/3, or you can write that as a mixed number if you'd like. So that's how we apply the properties. Okay, moving on to sandwich theorem. The sandwich theorem is used when you have a more complicated limit that can't be found by simply substituting. One that looks like example 4 on the next page. Looks like this, where if I were to plug 0 in for x, I would end up with 0 times an undefined value because I can't divide by 0. So this limit, for example, I would not be able to find by using substitution. So instead, I would use, for that particular example, I would use sandwich theorem. And so what that theorem states is the following. So if you have 3 separate functions, but I want you to pay attention to the one in the middle. That's kind of the one we're finding the limit of, where this function is consistently less than the h of x function and consistently greater than the g of x function for all x, excluding c, we'll just exclude that one, in some interval around c. That interval, by the way, would be on the x-axis. And I think the word on would kind of sound better here. So on some interval around c. Okay, so for all these x values around c, not equal to c, f of x, the y values are less than, the y values of f are less than the y values of h and greater than the y values of g. So if that scenario happens, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x, we'll just call that L, well, then that would imply, so this little arrow, double line arrow, that means implies that the limit as x approaches c of f of x is also equal to L. So that's what the sandwich theorem basically says. To give you some sort of a picture of what that would look like, let's say you had, here's our x-axis. And let's just let this be our interval here. So let's just let this be an interval from A to B. Interval is just a duration or a distance of x values. Let's go ahead and put c right in there. So let's say that the f function kind of goes like this. That's our f of x. And let's say our h of x, the one whose values are greater than f of x, kind of goes like this. That's h of x. And then g of x looks something like this, let's say. So notice on this interval of x values around c, all the y values for f of x, that's these guys in here, are all less than the y values of h of x and greater than the y values of g of x. And notice that as they approach c, so here are the x values are approaching c, the h of x function is coming down this way. In fact, let me make it more exaggerated. Have it touch right there. And then the g of x function is coming up toward the same value. G of x function is coming up toward the same value that the h of x function was coming towards. Well, notice how they're squeezing the f of x function or sandwiching the f of x function in between them. And so whatever that y value is right there, h of x is approaching it, g of x is approaching it, and together they force f of x to approach that same value. And that's basically what sandwich theorem is saying. Let's go ahead and try using sandwich theorem with example 4. And I'm noticing my examples are all out of order, so I apologize for that. Okay, this is telling me to use the sandwich theorem, and if you're ever told that, that means you need to follow a series of steps that I'm going to go through carefully, because I want to make sure I set up the condition for sandwich theorem to be able to use it to find this limit. First of all, what we need to understand is f of x is that function inside the limit. So f of x is the x squared times cosine of 1 over x squared. What I need to be able to do is figure out what the g of x and the h of x are. Well, that's not obvious. That is not an obvious statement. So what we're going to do is begin with something that is obvious. I'm going to take the trig part, the cosine part, and I'm going to recall that that cosine of anything, even though it's kind of complicated in there, it doesn't really matter. Cosine of anything is never greater than 1 or less than negative 1. So that's what I'd like you to begin writing. Let me leave some room on the left there. Cosine of anything, which in this case I'll use what was here, 1 over x squared, is always going to be less than or equal to 1, and it's always going to be greater than or equal to negative 1. Because if you recall, the graph of cosine looks like this. It never goes above 1, and it never goes below negative 1. So it's always in between 1 and negative 1, no matter what the inputs are. Okay, so down here I'd like you to write, set up compound inequality using the trig function. So by the way, this sandwich theorem works mostly with trigonometric functions because they are the kind of functions that oscillate back and forth. In fact, maybe we'll just take a pause right here and look at what that graph looks like on our calculator. So I'm going to go ahead and just type in the equation that was there, x squared times cosine of 1 divided by x squared. Okay, so there we have our equation. And I'm going to go ahead and hit zoom 7 because that's the trig viewing window. It kind of sets your axes up to match more of the trig function. So there, that's what our function looks like. And if I zoomed in a little bit, then I could maybe see more of that oscillation going on. So you can see a little bit more how it sort of oscillates here. And it looks like it's being sandwiched by something. What we have to do is figure out what it's being sandwiched by. So we start by just taking the trig part and putting it between 1 and -1. Okay, the second step then is I want to make this middle part match whatever f of x was. And I notice f of x is also being multiplied by x squared. So I'm going to take my original equation in part 1 and multiply everything by x squared. So that's step 2, is add in the remaining parts of f of x to all 3 parts of the compound inequality. So I end up with negative x squared is less than or equal to x squared times cosine of 1 over x squared is less than or equal to x squared. So that's step 2. Now, clearly I have f of x in the middle because this now matches what was here. And I have a function on the right. That'll be my, I think it was g of x from before. Oh no, sorry, we were calling that one h of x. And then over here I've got my g of x. So now I know what h of x and g of x are. So then the third step is to find the limit of those functions as x is approaching 0. So I'm going to take the limit as x approaches 0 of g of x, which was negative x squared. Now this is just a simple polynomial. It's just x to a power, so I can just plug 0 in there and I would get 0. And then I'm going to find the limit as x approaches 0 of h of x, which is x squared. Similarly, x squared is a polynomial. I would just substitute 0 in there, and my answer would be 0. So step 3 is to find the limit as x approaches c of both the greater and lesser functions. So find the limit as x approaches c of both the greater and lesser functions. The one that was on the far right and the one on the far left. Now those functions will be simpler. That's the whole point of sandwich theorem, is those functions will be a lot simpler than the garbage in the middle. And in order for sandwich theorem to work, they have to be equal. If you come across a situation where they're not equal, then you're not going to be able to use sandwich theorem. Okay, so then step 4 again is only doable if the limits in part 3 are the same. So then if they are, what we've basically done is we've set up the conditions for sandwich theorem. So if you recall, sandwich theorem said if you have a function in between 2 other functions, and the limit of those 2 other functions that it was in between are equal, it then forces that middle limit to be the same value. And so what we have here, I have this function is my f of x. And it's less than or equal to x squared, that would be my h of x. And it's greater than or equal to negative x squared, that would be my g of x. And the limit of g of x and the limit of h of x, these guys here, are both equal to the same limit, which in this example is 0. So then you would say for step 4, therefore, by sandwich theorem, and yes, you have to say by sandwich theorem, the limit as x approaches 0 of the middle part, the f of x part, must equal the same thing as the left and right limits did. So it would also equal 0. Because these two sandwiched it together, squeezed it in to cause that limit to be 0. And if we look at the graph on our calculator that we had earlier, I'm going to go ahead now and I'm going to type in what my h of x function was. That was x squared. And my g of x function was negative x squared. Let's take a look at what that looks like. So there's my h of x and there's my g of x. And notice how they are squeezing the f of x values in to meet at 0, just like both of them did. H of x was coming down to 0, g of x was coming up to 0, f of x was oscillating, and it got squeezed to approach 0 the same time that h of x and g of x did. And so that's sandwich theorem. So that last step was to basically state the conclusion that the limit of f of x equals whatever limit you found in part 3. Sorry about that. Okay, so make sure you study those 4 steps because there will be questions that come up on quizzes and tests. If you're missing one of these steps, you would miss some partial credit. So please study them, review them, and then you can kind of see what they look like with this specific example. For other unique cases, we are going to fall upon this special limit here, and that special limit is the limit as x approaches 0 of sine x divided by x. I'm going to just give this limit to you. That's why I'm calling it special. You're not going to have to prove it or anything like that. You just need to remember it. And so let's just see what would happen if we tried finding this limit by substitution. If I tried finding this limit by substitution, I would plug 0 in for the x in the numerator and 0 in for the x in the denominator. And already that's a big no-no because I'm dividing by 0. And then sine of 0, if you recall from pre-calculus, is just 0. And so I'm left with 0 divided by 0, which some might mistakenly think that's 1 or undefined or something like that. Well, the word that's been chosen for this situation is just called indeterminate form, meaning I cannot determine from that what the value is. There is a value, as it turns out, but I cannot determine what that value is by simply using 0 over 0. So in that situation, what I want you to remember are these 3 words: needs more work. And we'll see what that more work turns out to be. In this case, that more work is going to be looking at the graph. So if you could go ahead and take your calculators out and look at the graph of that equation. So I will have sine x in the numerator divided by x. And I'll just stick with the same trig settings as before. It looks to me that as x approaches 0 on both sides, so I have right side and left side, as x approaches 0 from both sides, it looks to me that the y values are approaching 1. And so let's go ahead and take a look at the table. So if you hit second and then this graph button, it'll take you to the table. And it looks as x is approaching 1 from the left and as x is approaching 1 from the right, these values sure enough look like they're approaching 1. Can't tell exactly what it is at 0 because the value is indeterminate at 0, but it looks like the y values on the right and left were wanting to approach 1. And so that limit will just be given to you. Just know that whenever you have the limit as x is approaching 0 of sine x over x, that value is going to be 1. Given. And while we're on the subject of given limits, I want to tell you this limit as well, which is the limit as x is approaching 0 of cosine of x minus 1 divided by x. This is going to come in handy at the beginning of chapter 3, but I figured I would just give it to you now so you could memorize this one along with that. These are going to be our 2 special given limits. So just like with the last one, if you were to try and find this limit by substituting, I would plug 0 for x in the numerator and then 0 for x in the denominator. And if you recall from pre-calculus, cosine of 0 is 1. And so again, I'm left with an indeterminate form. I'm left with 0 over 0. I am not able to determine from this what that value is going to be. So it would need more work, just like the last one. So I'm going to go ahead and look at the graph of this quotient as well. So if I take a look at the graph of cosine x minus 1 and then divided by x, it looks to me, again, just like the last one, that there's a very clear limit there. As the values of x are approaching 0, it looks like the y values are wanting to come together at 0. And if I go to the table like I did last time, these values, sure enough, are creeping towards 0 on both the left and the right. Of course, it's not defined at 0 because it's indeterminate there, but it looks like those y values are wanting to get closer to 0. And if you look at the graph, that's exactly where they're wanting to get close to. And I know you can't tell here, but there's technically a hole right there at 0. It's just really hard to see with our calculator. So this limit that you are allowed to just sort of remember and use is 0. Now, question is, how do I use that? Why does that matter? The reason that matters is because you might have something more like this, and you're asked to determine the limit algebraically, and then, of course, verify graphically means you can check by graphing, but I want to see the work algebraically. Now, I'm going to use those special limits combined with the properties of limits to be able to do this. So right now, if I tried substituting, so I always try that first, because if it works, awesome. So if I substituted first, I'd have 0 plus sine of 0 all over 0, and that again leaves me with 0 over 0. So that doesn't mean the answer doesn't exist, it just means I need to do more work. Needs more work. So in this case, my more work is going to be rewriting this as a sum. I'm going to have x over x plus sine of x over x, which is correct because I have a common denominator, so I can just turn that into a sum of two different quotients. Well, this quotient right here is just going to equal 1. So really what I have is the limit as x approaches 0 of 1 plus the limit as x approaches 0 of sine x over x. Because the sum property says that I can take the limit of the two functions separately. Well, notice there's no x's here. This right there, that number 1, that's just the function that's a constant. If I were to sketch the graph of this, it would just be a straight line at 1. So this limit is just going to equal 1. So this is going to equal 1 because it doesn't change. It's going to be 1 on the right, 1 on the left. It's never anything other than 1. We just learned this special limit. This special limit is always equal to 1. And so I have this limit of 1 plus that limit of 1 makes 2. And so that's the answer for part A. Okay, part B is, I just threw it in here. It doesn't use the special limit we just learned, but it is a unique case in that if I tried to substitute first, and especially this one I would want to substitute first because it's polynomial divided by a polynomial. It's rational. So if it's rational, then as long as the denominator is not 0, I can just find the answer by substituting. So I plug in 1 in the numerator and I plug in 1 in the denominator, and unfortunately I end up with that 0 over 0 again. So this needs more work as well. But there's no sine x over x in here that I could use that special limit. So what I'm going to try here is factoring and then see if anything can cancel out. So in the numerator, I have x minus 1. In the denominator, if I factored, I would have, these two factors, 1 of x plus 1, 1 of x minus 1, because we have a difference of squares. So I can see that these here will factor. Now just keep in mind, x is not allowed to equal 1 in order for me to factor. But we learned last lesson that I don't need to let x equal 1. I don't care what happens at 1. I just want to know what's happening on the right and left of 1. So this cancellation then is okay for me to do because, again, I don't care what happens at 1. I just care what happens around 1. Okay, so around 1, the function looks like this. So I can just plug. Now I can just evaluate by substituting. And the answer for part B would be 1/2. So I wanted to kind of keep track of what we've been doing so far. What to do if you get a 0 over 0 from substitution? Well, that means you need more work. It doesn't mean stop. So notice what I did in part A was I used my special limit. Or also I split into a sum. So you could try splitting into a sum or a product and see if your special limit applies. That's one option. Notice when it's a polynomial, like in part B, then you're going to want to see if you can factor and cancel. Okay, but there's a bunch of other weird situations that come along sometime. One of them is when you get something like this. For example, the limit as x approaches 1 of 1 minus the square root of x all over x minus 1. In a situation like this one, I would recommend rationalizing the numerator. So if you have something like this, you're going to want to try to rationalize the numerator, which I know seems weird. We're not used to doing that, but you'll see in calculus it has to happen from time to time. So I would first rationalize the numerator, and whatever you multiply at the top, got to multiply at the bottom. And that would leave me with the limit as x approaches 1 of, after foiling all of that, I would end up with 1 minus x divided by x minus 1 times 1 plus the square root of x. And I can see that these factors are almost identical. They're just opposite order of subtraction. So if I factored out a negative 1 from the numerator, that would turn this into a positive, and then that would turn that into a negative. And then they would be identical. And then I could cancel them like that, again, as long as x is not equal 1. But we're not going to let x equal 1. We're just going to look at around 1. And then I'd be left with this. And then I could go ahead and substitute. And so the answer for this complicated looking limit turns out to be rather simple, negative 1/2. So if you come across something like this and you go to substitute and you get 0 over 0, try rationalizing the numerator. Another kind of weird situation is when you have to deal with the greatest integer function, which is referred to as INTX. So just as an FYI, INTX is the same as this function you might have learned in pre-calc with the brackets x. It's basically the greatest integer function. And it's the function that basically says for whatever x you plug in there, the corresponding y value will be the greatest integer, not greater than that x value. And so you end up with a series of steps that look like this. So by the way, on your calculator, I'll clear that. If you go to math, number, that's where you have the INT function, or the greatest integer function. Let's just go ahead and take a look at that function and what the graph looks like. And for this, I'm going to go ahead and put my graph into dot mode. Right now it's in connected mode. Dot mode will make it so that the steps don't connect. They'll actually make legitimate steps. So let's go ahead and take a look at this. So this is our step function. So when x is a value between 0 and 1, the greatest integer function rounds that down to 0. Oh, this is in trig. This is trig right now. Let's go to zoom 6. There we go. So when x is between 0 and 1, the y values are rounded down to 1. When x is between 1 and 2, the y values are rounded down to 1. And then it sort of goes on like that. So this example here that I wrote down is asking us to find the limit as x approaches 3 from the right of the greatest integer function. Well, I could just substitute it in, but here's the thing. If I tried substituting, I would have INT of 3, and that's equal to 3. Okay, so let's take a look at our graph, if you will, and see if that's what's happening on the right of 3. So let's take a look at the graph. So as x is approaching 3 from the right, the y values are in fact at 3. So that is in fact correct. Not a problem. Substituting worked. However, if this had asked instead for the limit as x was approaching 3 from the left, well, it would be a different story. I would not be able to find that out by substituting. Because if you look at the left of 3, so if you're coming toward 3 from the left right here, the y values are at 2 because they haven't been able to reach 3 yet. They've been rounded down to 2. And so sometimes you have to look at a graph in order to see a limit. So for this one, I would say sketch the graph. Now, if you forgot what the graph of intx looks like, our greatest integer function, the other option is to plug in x values that are close, very close to the value x is approaching. So plug in x values that are close to, I'll put the c value, which in this case is 3. So let's say you don't know how to sketch the graph of intx, but you remember what it means, and you're approaching 3 from the left, so you might want to make a little table here. And you could say, all right, well, what happens at 2.9? That's really close to 3 on the left. Well, if I plug that into the greatest integer function, that would actually round it down to 2, because 2 is the greatest integer, not greater than 2.9. So then you could say, all right, what about 2.99? Plug that into the greatest integer function and recognize that that would be rounded down to 2, and so on and so forth. And then you could really realize as x is approaching 3, really close from the left, the y values are approaching 2. So these are just some tricks of the trade in case you come across some book problems that don't work out nicely, that end up with 0 over 0. These are things we can do to find those limits. And I will see you in class.